Hello everyone. So today we will talk about an introduction to logistic regression. Logistic regression is an important topic in data analytics and for decision making. In real world you will use logistic regression a lot. That's why I decided to cover this topic. However, we're not going in depth of how logistic regression works because there are a lot of details. We will touch basically just the basic logistic regression and you will learn how it actually works. So logistic regression is a classification method and it's different from simple regression and multiple regression that you learned earlier. In simple and multiple regression, the response variable was a continuous or numerical variable, but here our dependent variable or response variable is a dummy variable, and we also call it a logic variable. And what we mean by logic is it has two values, can be yes or no, true or false, success or failure, and so on. So the dependent variable or response is modeled as a Bernoulli random variable, and you can think of success or failure or true or false. Y, which represents the response variable to be 0, or it can be 1. So we can actually switch this, but let's say y equal to 1 represents success, and if y is 0, it represents failure. So an example can be you are evaluating a loan application and you want to see if this loan application is approved or it has to be accepted. And that can be based on, if we use a logistic regression, we can say if there is there's a high probability that this applicant will default on the loan or will not default on the loan. So if there is a high probability that default will happen, you will not give that loan, and otherwise you will probably give that loan. Okay, so we seek to predict the probability of a success outcome of the dependent variable or response variable y. Predict probability that the loan defaults, or in other words, PR represents probability of y equals to 1. The probability of success, in parentheses, success here means the default in the loan. So the probability of success is a particular function of independent variables or explanatory variables, x1 up to xp. So we can consider multiple specifically numerical variables as explanatory variables. And of course, if you are familiar with the topic of providing loan or mortgage, there are certain factor variables that you can obtain as data from your customers and decide based on the logistic model, you can decide to provide the mortgage or not to provide. So the model looks like this. Of course, you don't have to work on the details of mathematical part because JMP will actually solve everything for you. But understanding how it works is not bad. So and it's okay. You will never have to manually input values in it. So probability of default y or response to be 1 given for a specific value of x, and x, when we say x, it means it can be x1 up to xp, right? Equals to the reciprocal of 1 plus e to power negative beta 0 plus beta 1 x1 plus beta 2 x2 up to beta p xp, where x1 up to xp are your explanatory variables, numerical, continuous, and beta 0 is your intercept, beta 1 to beta p, they are your slopes. Our data, of course, they can be y1, that is your first case that has defaulted or not, can be 0 or 1. x11 is your first client or customer with the first factor, for example, credit score, salary, income, right, and other factors, and that goes on and on for other customers or clients, previous customer or clients. Note that all of the yi variables are either 0 or 1, and 0 is that they did not default, and 1 represents that they did the default. So in a very general form, logistic function looks like this. And if we also put 1 plus e to the power w, it would be like this. It goes down. Really depends on the question, and you will see in the future how it looks like. So that's the model. And consider predicting the probability a widget will fail on an assembly line, right? Logistic regression coefficients, the intercept, beta 0. Let's say the answer comes out at -5. Number of foremen, -1. And temperature, let's say it's 0.02. So as an example, you can, same as simple regression model, you can have some intercept and some slopes. Probability of success with 1 foreman and 80 degree temperature would be, so all we have to do is to substitute beta 0, beta 1, and beta 2 into that formula right there, and just calculate, and whatever your answer is, that would be the probability of y to be 1 given for a specific value of x. The two logistic regression coefficients, remember, are beta 0 up to beta p, and putting them together we can call them all beta. How do we estimate the logistic regression coefficient? We will talk about that. Use the method of maximum likelihood estimation. So the key idea in logistic regression is to choose the coefficient values that maximize the probability of observing the given data set. As a result, we're going to have the probability of y equals to 1 given for a value of x, replace values of x, and then of course the opposite probability would be probability of y equal to 0, which is 1 minus the probability of y to be 1. And the likelihood, or the probability, the total probability based on beta, x, and y, as explained in the previous slides, would be equal to the probability of y to be equal to y1, x to be equal to x1, multiplied by probability of y equal to y2, given that x is x2, and y1, x1 are conditions of the first client, second client, third client, up to n client. So we have this historical data from our past customers, and of course they are independent because each customer gets in based on their background, based on their information. We can decide to give them loan or not. So if we give them loan and they default, that would be a 1. If they don't default, the y would be a 0. So considering the model that we learned earlier, we can actually generalize that formula here, but I'm not going to go into the details of this. So remember that we can also use log function, and what log function does is to change multiplication to adding. So that's where you have addition here. And the power yi and 1 minus yi can become a coefficient yi and 1 minus yi. Okay. So we're going to go over a simple example, and I will show you on PowerPoint how to interpret, and then later I will show you in JMP how to get results and interpret the results for yourself. So example we'll work on is predicting loan repayment with logistic regression. The simple lending decision tree can be created if the borrower defaults, and that's the probability we're calculating. What's the probability that the borrower defaults, right? And if that happens, the lender loses $4,000. If the borrower does not default, which is 1 minus p, the lender makes $1,000. So of course, we want to find out for each applicant using the model we create using logistic regression. We want to predict and say this applicant has a high probability to default or not. So identifying loans that are bad risk. So remember, the numbers I represent here, they're not necessarily generally correct. They're just specifically explained here. Based case by case, depends on companies and type of customers they have, type of loan they provide. These numbers can be different. So a loan is a good risk if we expect to make money from it. Good risk, or in other words, low risk, right? So corresponds to a low probability of default. A loan is a bad risk or high risk if we expect to lose the money from it. Corresponds to high probability of default. From the decision tree, our expected profit from funding the loan would be $1,000 times 1 minus p, the probability that your client does not default, minus $4,000 multiplied by the probability that your client does default. So the higher the probability p, the higher loss you have. Using arithmetic, the break-even point can be calculated at 0.2. Again, $1,000, $4,000, these are just an example, and the 0.2 is also just for this example. They're not a general rule here. So a loan with default probability below 0.2 or 20% is a good risk or low risk. A loan with default probability above 0.2 or 20% is a bad risk. We should only fund a loan that is good risk or low risk. Loan decisions can normally be made based on character, capacity or cash flow, collateral, capital, and conditions. So what happens is the loan application comes in. We use our likelihood model or regression model to decide the probability of default, and if that probability is low enough, we will do the funding decision. We will say yes. If it's high, if it's a high risk case, we will say no. So the dependent variable can be our or the response variable can be default, the probability of default, whether the loan was not fully repaid. So based on our data, we collected some data and randomly actually reduced the data to smaller sample of something about 400 data. And we already know this is historical data about our previous customers that they finished paying off their loan. So we know that they have paid or not. If they have fully paid, the response variable would be 0. If they did not fully paid and they default, that would represent by 1. Independent variables, standard measure of credit worthiness. So these are actually factors that we can use. In this example, I will use a FICO score and annual income. So credit worthiness, monthly loan installment, annual income, FICO score, revolving balance, number of inquiries in the past 6 months, and number of deleterious public records. So let's say we have already run our logistic regression, and let's say these are our results. So we have our intercept, beta 0, beta 1, beta 2, beta 3, beta 4, beta 5, and beta 6. How do we interpret this? First of all, this is how the model looks like. The probability of default for a given value of x would be 1 over 1 plus e to power negative 10.015 right there, plus 0.001 times 366, and this is for a specific value of x. Okay, so this is a specific case with $366 monthly installment, with log annual income of 4.5, with a FICO score of 682, with a revolving balance of $7.5 thousand. Inquiries in the past 6 months was 1, and delinquent public record, none. So if this case come to your table, you want to decide to provide or give loan, approve the loan or not. The coefficients go there. The values of x1 to xn goes there. So we just arrange them here and we calculate that. The probability of default is 21%. This 21%, based on the rule we said 20%. So the answer would be no, we should not consider this person. But of course there is upper and lower confidence level, and we can always think about if we can get more information about the customer and make a right decision. Applying a model to a new loan applicant. So as we just said, if you plug in the numbers, and this notation of course is a good way of notation for new customers. So you have a new customer with information. So the y new is what we are going to predict. So this is a new customer. We don't know they're going to default or not. So the y new is going to be, the probability of y new to be 1 is going to be calculated by the regression model, the logistic regression model we created. This notation is cumbersome. Just remember that the logistic regression model give us predicted probability values that don't always represent the true probability of the corresponding event. And what that means, this is a probability calculated. It's not 100% correct. It's not 100% accurate. So up to a certain point, maybe 90%, 95%, depends on how you want to work with it, how you decide to create a model, and how you want to use it. It's accurate up to a certain point, not 100%. So how do we interpret results? For example, if we want to use the slope of number of inquiries in the last 6 months. If none, the probability is 0.189. If just 1, 0.2, and so on. So the inquiries in the last 6 months has positive coefficient in this case. And the coefficient, if you remember, was beta 5 was 0.137. If you look here, 0.137 right there. It's inquiry in the last. That's your coefficient, or that's your slope. That's the slope. Higher value of variable will result in higher value of probability or higher probability of default. So the more number of inquiries in the last 6 months results in higher risk, right? Lower value of variable will result in a lower value of probability. Consider the probability of default for applicants with different numbers of inquiries. Another example is the log of annual income, which has a negative coefficient. So in this case, it's a negative coefficient. Let's see how we can interpret it. The higher variable value yields lower probability estimate or lower risk of default. So when you have a negative slope, beta 1, beta 2, any of those beta, what that means is, if that variable is higher, that reduces the risk of default. Lower the variable values yield higher probability estimates. Consider estimated default risk for applicants with different annual income, but all other variables as in earlier slides. So next is interpreting the coefficients using odds. And this is not 100% necessary, but this is one way of interpreting results. So what are odds? So odds of y equal to 1, or odds of default, is the probability of a default happens divided by probability of default does not happen. This means probability of default happens, and this is 1 minus, or the opposite, which is it means it doesn't happen. So an event with probability close to 0 has odds close to 0. An event with probability of 0.5 or 50% has odds equal to 1. Because this is 50% divided by 50%, that would be 1. An event with the probability close to 1 has a very high odd, because this would be close to, like, let's say 0.99. The denominator would be 1 minus 0.99, which is 1%, or 0.01. Of course, 0.9 divided by 0.01, that would be a big number. So the higher the odds, of course, we have a higher probability of default or risk. But again, if odds is 1, that means there's a 50% chance on both sides. Interpreting coefficient using odds. So inquiries in the last 6 months has positive coefficients. We just said about the example beta 5, 0.137. Higher value of variable will yield higher odds. Lower value of variables will yield lower odds. So this makes sense, right? For every increase in one unit, or increase in inquiries, keeping all other variables constant, odds is multiplied by e to power 0.137, which is 1.1. The opposite, if beta is negative, like the log of annual income, right? The higher variable values yield lower odds. Lower variable values yield higher odds. For every increase in, or every 1 unit increase in at the annual income, keeping all other variables constant. Odds is multiplied by e to power negative 0.96, which is almost 0.38. And this is the opposite, right? This is negative. So if you paid attention here, the 1.147, so the 14.7% higher than 1, 14.7% higher than 1, that's the risk. And here is the opposite of this number. This is 38%. Opposite of 38% is 62%. Using odds, we can make simple statements to interpret the logistic regression model's coefficients. Step 1 is look up for a coefficient B in the regression summary output. The coefficient for monthly installment B1 is 0.00113. We can calculate e to power b, which is 1.001, and the interpret using odds would be holding all other variables constant. Each $1 increase in the installment size yields in a 1.00114 time higher estimated odd of the default. So the model gives estimates of the probability of default. How can we use the model to predict who will default? Try to answer these questions. A sensible approach: for a given individual, compute their probability of default using the model. So again, the numbers provided here, they're not a rule of thumb. Depends on what company, what type of loan, what type of customers we have. These numbers can be different. Now let's work on JMP data. So this is our data. It's bankloan.jmp, and you can find this from Canvas under your files and data folder, and just open it. So there are lots of information about our clients, customers, city, state, zip code, bank, approval date, terms, and gross income, annual income after deductions, credit score, and did they default or not. So if they default, it's a 1. If they did not default, it's a null or 0. Now we can use analyze. Remember that when you want to start, make sure your default is considered categorical variable under JMP. So go right click, go to column info, and make sure this is character, and make sure this is nominal, and click OK. Then let's use analyze fit y by x, or we can also use fit model, doesn't matter. So default is our response variable. Remember I said that in logistic regression we want the logic variable or categorical variable, group variable, or dummy variable goes to response or y. And let's run this analysis using the credit scores. And what's our target level? Our success here is considered as default, which is 1. So remember to set that correctly so you get the right results. Click run. So based on the model we have here, you can see that is our logistic regression based on the chi-square test, created that line. So you can see the higher the credit score, this is the probability, right? Probability of what? Probability of default. So the lower probability of default. Higher the credit score, lower is the probability of default. Okay. Is this model that we have here, is this model a significant model? So we can look for whole model test and check the chi-square p-value right here. P-value is less than 0.05, so this is a significant model. With the R-square of 0.24, 24.7% of the variation in default being determined is explained by the credit score. Of course, there are other variables that can help to increase that amount of R-square. So if you create multiple models, the AIC also can help you to decide which model has the lowest error and is a better model. So AIC represents a calculation of amount of error, represents amount of error in the model. So if you have multiple models, you can compare their AICs and decide which model has higher R-square, which model has lower AIC, and which model has a better p-value. That model would be your model to go for. And this is the parameter estimate. So the intercept is 6.33. It's significant. The credit score slope is 0.0115. That is significant. Let's see. And so we have the chi-square values, standard error. So this model is significant, and we can see that those that have higher credit score, they have lower probability of default. Let's see if we can find some of those prediction formulas here. So click on the red triangle. So this is where you can find the confidence intervals, and you see here it says save probability formula. That would give us the formula of the probability, so we can create some predictions here. So if you click on this, look on the right hand side, here is empty. When I click on save probability, that probability and predicted values will appear right there. Perfect. So right here, line 1 is the predicted, which means if you plug in credit score, specific credit score, into the formula, into the logistic formula, and where's the logistic formula? It's right there. 6.33, negative 0.01. You plug these into the logistic model. So that would be your default would be predicted, or let's say it's a score. And probability 1, and we have also probability 0. Probability 1 is probability of default. So the first customer's probability of default was 3.5% or 3.6%. Second, this is 8%, 8%, 4%. So you can see that these are low. And probability of not defaulting, 90%. We'll go down to see if we have lower probabilities. Example here, this case is 21% probability of default, 21% also here, and 78% probability of paying back the loan. Interesting, this one. 42% probability of default, If you want to use 20%, then that would be a person who you would not give them. Another thing we can add here is the confusion matrix, and the confusion matrix shows us here, based on the predicted formula, based on the logistic regression formula, what portion of those actual cases were correctly predicted. So if they were 1, means they had defaulted. How many of them correctly were predicted to default? 62 of them. How many of them were not predicted correctly? 54 of them. If they did not default, how many of them were incorrectly considered they will default? 37. And if they did not default, they actually did not default, how many of them were considered they did not default? 250. This is correct. So 62 plus 254. Okay, so this is a word file. Let's just type in. The correct predictions are 62 and 254, because 1 is predicted 1, 0 is predicted 0, right? So that would be 62 plus 254 divided by the total. How many of them we have? So we have all of them together are 62 plus 54 plus 37 plus 254. If you use a calculator, that would be equal to 0.7764, which means the performance of this logistic model is 77.6%, which means it correctly identifies defaults by 77.6% accuracy. Okay, that's how accurate this logistic regression model is, based on the historical data that we just created. Example here, and this example is based on years of experience. That's your explanatory variable, that's your independent variable. And you also have completed tasks. So what completed task in this example is, we're having an interview session, and we have applicants who are interviewees, and they attend interview session. And during the interview session, what we do, we give them a task, and we want to see if they can complete the task during the time given. We give them 10 minutes time. If they complete the task, we put yes. If they don't complete the task, we put no. And what we are interested to know is, based on years of experience, can we predict and say and find the probability of a candidate can complete the task or not. Maybe that in the future reduce a lot of work in interviewing process, and we can actually filter our candidates based on logistic regression. So let's go to analyze, fit model, and chose, of course, completed task is a logic, has 2 variables, has 2 groups, yes or no. Target is, we want to see those who complete the task, right? And years of experience. Okay, click run. So the results seem to be significant. We have a significant model, and you can see the higher the years of experience our candidate had, the higher the probability of completing this task. This is the probability of completing the task, right? The higher years of experience, the higher the probability of completing the task. And this model is a good model. R square is 9.8%, AIC 54. So let's see what else we can. Also, this example is available on Canvas. So download the data and just practice using this data. Okay, so that would be all for our logistic regression. Logistic regression actually can have more details. We can have different types of logistic regression models that we did not discuss here. If you were interested, ask for a reference and I will give you some books or some websites to just look for and learn more about logistic regression and its importance. Logistic regression is one of the methods that's used in machine learning, which help make decisions, especially for advertising, online advertising. Machine learning is used a lot.